Hello everyone. Welcome to Blacksnwhite.com. Suppose you are in charge of setting up a new data center for a global company. You must decide on the network model that best supports internal communications and client-facing services across continents. You have several models to choose from: the OSI model, which is detailed in layer, or the TCP/IP model, which is streamlined and widely used. How would you evaluate the pros and cons of each model in terms of scalability, security, and ease of troubleshooting? What specific needs of your data center should guide your choice between these models? This is where network models come into the picture. Let us learn about it. The learning objective of this topic are as follows. Define the network models, discuss the OSI model, describe the TCP/IP model. Network models are essential for understanding and designing communication systems as they provide a structured framework that standardizes how data is transmitted across networks. Dividing complex processes into distinct layers, such as those in the OSI or TCP/IP models, makes troubleshooting protocol development and interoperability between devices and technologies. More efficient network models ensure compatibility between hardware and software from different vendors, enabling seamless communication across diverse platforms. Also, they facilitate scalability and innovation by offering a clear blueprint for implementing new protocols and technologies. Network models are the backbone of networking, supporting the design, implementation, and maintenance of reliable and efficient communication systems. When discussing network models, we generally look at two main types based on their layered architecture and functional categorization. The OSI Reference Model and the TCP/IP Reference Model, also known as the Internet Model. Each model provides a structured framework for understanding and designing network communications. The OSI Open Systems Interconnection model, established by the International Standards Organization (ISO), represents a foundational effort aimed at global standardization of the protocols used in network communications, initiated as a structured approach to networking. This model was revised in 1995 to better address the needs of diverse systems and enhance interoperability. This model, called ISO-OSI, emphasizes open systems, specifically designed to facilitate communication across different networks and platforms. The OSI model lays out a 7-layer architecture that standardizes functions at each layer, enabling network systems to communicate effectively regardless of their underlying hardware and software configurations. This model helps develop network technologies that are compatible across various systems and supports the creation of more scalable, reliable, and secure network infrastructures. The image, understanding network interactions across 7 layers. This model is depicted in a scenario where a host A and B communicate through these layers. Each layer, from the physical to the application layer, handles specific aspects of network communications, ensuring data is passed seamlessly from one layer to the next. The figure shows the vertical flow of data through individual layers of a single host, and the horizontal data transfer across similar layers between two hosts facilitated by routers and protocols at each level. Protocols within each layer govern how data is formatted, transmitted, and processed, ensuring interoperability between network systems. The structured approach helps diagnose network issues, design systems, and ensure data integrity and security across complex networks. The structure of the OSI Open Systems Interconnection model, which organizes network communication into 7 distinct layers. This model is a conceptual tool used to understand and design network systems by breaking down their functionalities into layers that range from physical hardware, physical layer, to application layer. The layers include, from bottom to top, physical data, link, network, transport, session, presentation, and application. Each layer serves a specific purpose, handling aspects such as physical signaling, data transfer, routing, data integrity, session management, data representation, and user interaction through applications. This layered approach ensures standardized communications and interoperability between diverse network technologies and platforms. Next is the physical layer. This layer is responsible for transmitting robots from one node to the next over a communication channel. The physical layer facilitates the transfer of raw binary data streams across physical mediums between nodes in a network. This transmission involves converting data into electrical, optical, or radio signals that can travel over the selected communication channels. It deals with the mechanical and electrical specifications of the interface and transmission medium. The physical layer is concerned with defining how devices physically connect to the network and the nature of these connections. This includes the layout of pins, voltages, cable specifications, and other physical requirements necessary to establish and maintain a reliable link. It also defines the procedures and functions that physical devices and interfaces must perform for transmission to occur. This layer outlines specific operations that must be carried out by physical devices such as modulation or signal conversion. To ensure successful data transmission, it prescribes the timing of signals, synchronization of bit streams, and the configuration necessary for data encoding and decoding at each end of the transmission. The image you've shared outlines various aspects and functions of the physical layer in the OSI model of network architecture depicted in a hexagonal diagram surrounding the central label physical layer. Each hexagon represents a specific rule or feature managed by the physical layer. Transmission mode refers to the method by which data is transmitted between two devices, which could be simplex, half-duplex or full-duplex. Physical topology describes the arrangement of the network's various elements like nodes, links, and devices, and how they are physically or logically connected to each other. Line configuration deals with how devices are connected in the network, whether point-to-point, multi-point, or some other configuration. Physical characteristics of interfaces and media specifies the mechanical, electrical, and operational characteristics of the interfaces and media. Representation of bits involves the encoding and signaling of bits over the physical medium. Synchronization of bits ensures that the transmitter and receiver are synchronized, which is crucial for the proper decoding and processing of the received signals. Each hexagon contributes to the overall function of the physical layer, which is fundamental in facilitating the transmission of data across a network. The data link layer plays a crucial role in error control by detecting and correcting any errors that may occur during data transmission between nodes. This ensures that the data received at the destination is consistent with what was sent, enhancing communication reliability. Also, the data link layer manages flow control, which regulates the data transmitter rate between two nodes. To prevent a fast sender from overwhelming a slow receiver, this control helps maintain a smooth and efficient data transfer rate, avoiding potential bottlenecks in network communication. This layer also transforms the physical layer from a raw transmission facility into a reliable link. It does this by structuring frames out of the stream of bits received from the physical layer, ensuring the data is packaged and addressed correctly for the network. By providing these essential services, the data link layer enables the physical infrastructure to support a more error-free and regulated data transmission environment, which is critical for maintaining the integrity and efficiency of network communications. The functions of the data link layer in a network. The key responsibilities of this layer are as follows: error control. The data link layer's ability to detect and correct errors during data transmission. It ensures that duplicate frames are recognized and any damaged or lost frames are omitted. Maintaining data, communication, integrity, flow control. This function depends on the synchronization of data transmission speeds between the sender and the receiver. It prevents the sender from overwhelming the receiver by adjusting the data flow to match the receiving capabilities. Access control. The access control indicates the layer's role in determining another leaf highlights this function, which devices control the network at any given time. This is crucial in shared network resources to avoid data collisions and ensure smooth traffic framing. This represents dividing the data stream into smaller, manageable units called frames. This structuring allows for effectively handling and transmitting data over the network. Physical addressing. This function involves defining the sender and receiver of each frame with physical addresses, usually MAC addresses. This ensures that each frame is delivered to the correct destination within the network. The network layer is primarily tasked with ensuring that packets are delivered from their source to their destination across multiple network links. While the data link layer handles the transfer of packets between two systems on the same network, the network layer steps in to manage packet delivery over the entire journey from start to finish, regardless of the number of networks the data traverses. Also, the network layer addresses several other critical functions. Logical addressing. This involves assigning IP addresses to devices to uniquely identify them on a network, facilitating accurate packet delivery across different networks. Routing the network layer determines the best path for packet travel from source to destinations. The transport layer serves as a true end-to-end layer in the network stack, ensuring the complete and correct delivery of the message from one application process to another. An application process refers to any program that's running on a host such as a computer or server. This layer takes in data from the upper layers and, if necessary, breaks it down into smaller units before passing it on to the network layer. This segmentation helps manage the data efficiently across the network. The transport layer also ensures that all data segments arrive accurately and are really assembled at the destination, providing a reliable communication channel between processes. The key functions of the transport layer in network architecture. It highlights 4 primary responsibilities. Service point addressing. This refers to the transport layer's ability to manage communications between multiple programs on a single computer. It uses service point addresses, typically known as port numbers, to distinguish between different processes, ensuring the successful delivery of packets from one process to another. Connection control. The layer supports connection-oriented and connectionless transmissions, enabling flexible communication strategies depending on the network requirements and the data transfer types. Segmentation and reassembly. This function involves dividing a data stream into smaller segments for easier handling and transmission across the network. Each segment is assigned a sequence number, which helps in accurately reassembling the data in the correct order at the destination. Flow control and error control, similar to the data link layer, but with an end-to-end scope. These mechanisms manage the data transmission rate and check for errors across the entire transmission path from source to destination, ensuring reliable data transfer. The next layer is the session layer. The session layer enables users on different machines to establish and maintain sessions with each other. It plays a pivotal role in setting up, maintaining and managing the interaction between communicating systems, ensuring that communication flows smoothly and efficiently. In addition to these functions, the session layer also addresses dialogue control. This allows the session layer to manage the direction of communication between two systems, determining whether both can send and receive simultaneously or must take turns. Synchronization. The layer helps coordinate data exchange by placing checkpoints in the data stream. Following is a presentation layer. The presentation layer is responsible for representing and structuring information for transmission between two systems. It manages syntax and semantics to ensure that data transferred from one system can be correctly interpreted by another. Key functions of the presentation layer include translation at the receiving end. This layer converts incoming data into a format the recipient system can understand, ensuring that different systems can effectively communicate despite potential differences in data encoding. Encryption. This feature is vital for securing sensitive information during transmission. The presentation layer implements encryption protocols to safeguard data privacy, ensuring that information remains confidential and secure from unauthorized access. Compression. The presentation layer compresses data to optimize the transmission process, especially for bandwidth-intensive applications like multimedia streaming. This reduces the volume of data transmitted over the network, enhancing speed and efficiency. Final is the application layer. The image provides an overview of the application layer in networking, emphasizing its role and specific responsibilities. Core functionality. The application layer contains various protocols that provide user interfaces and support for network services. It acts as the bridge between the user and the underlying network infrastructure. Specific concerns include network. Virtual terminal enables remote access and communication between systems by simulating a terminal interface, file transfer, access and management. This function handles protocols for transferring, accessing, and managing files across the network, ensuring seamless data sharing and manipulation. Mail services facilitates email communication by managing protocols for sending, receiving, and accessing emails. Directory services provides access to network directory systems, which help organize and locate resources on a network such as usernames and addresses. Let us talk about the TCP/IP or Internet model. The TCP/IP or Internet model was developed before the OSI model and initially consisted of 4 layers. The host-to network or link layer, the Internet layer, the transport layer, and the application layer. The host-to network/link layer combines the functionality of the OSI model's physical and data link layers, handling the physical transmission of data and link-level communication. The Internet layer corresponds directly to the network layer of the OSI model, managing logical addressing and routing to ensure data packets are delivered across networks. The application layer in the TCP/IP model encompasses the responsibilities of the session presentation and application layers. In the OSI model, support from the transport layer facilitates end-user interaction, data format, and session management within a single layer, streamlining the process compared to the OSI model. We have the mapping of the OSI model with the TCP/IP model, highlighting the respective layers and key protocols within the TCP/IP protocol suite. The OSI model consists of 7 layers, whereas the TCP/IP model simplifies the structure into 4 layers. Process/application host to hosts, internet and network access. The process/application layer of TCP/IP combines the functionalities of OS application presentation and session layers. Supporting protocols like HTTP, FTP, SMTP, and DNS, the host-to-host layer corresponds to the OSI transport layer, handling reliable communication through protocols like PCP and UDP. The Internet layer aligns with the OSI network layer and manages routing and addressing using IP/ICMP and ARP protocols. Finally, the network access layer includes OSI's physical and data link layers, utilizing protocols like Internet Frame Relay and ATM for data transmission. The 4 layers of the TCP/IP model, each representing a distinct function in network communication, host to network/link layer. This layer corresponds to core, the physical and data link layers. In the OSI model, it is responsible for handling the physical transmission of data over the network, including device connectivity, hardware addressing, and managing access to the transmission medium, Internet layer. This layer is equivalent to the network layer in the OSI model. It handles the logical addressing, such as IP addresses, and routing of data packets across multiple interconnected networks, ensuring that packets are delivered to their intended destination even over long distances. Transport layer. This layer provides reliable communication between devices. It ensures data integrity and proper packet sequencing using protocols like TCP for reliable connections and UDP for faster connectionless communication. It also manages error detection and flow control. Application layer. This layer combines the functions of the application presentation and session layers. From the OSI model, it provides end-user services such as web browsing, file transfer, and email. Using protocols like HTTP, FTP, SMTP, and DNS, it facilitates direct interaction between the user and the network. The OSI and TCP/IP reference models share a common foundation. Both are based on a layered architecture that organizes communication processes into a stack of independent protocols. This design allows for modular development and troubleshooting, where each layer performs specific tasks and interacts only with its adjacent layers. While the functionality of the layers in both models is broadly similar, key differences exist. The OSI model is more detailed with 7 layers and serves as a conceptual framework for understanding how data travels across networks. It focuses on standardization and provides clear distinctions between functionalities like presentation and session management, which are separate layers in all, but combined in TCP/IP. In contrast, the TCP/IP model is simpler and more practical with only 4 layers: application, transport, internet, and network access. It consolidates several OSI layers, emphasizing real-world implementation and interoperability. Also, the TCP/IP model is closely tied to the protocols used on the Internet, such as IP and TCP, making it more widely adopted in modern networking. Despite these differences, both models aim to achieve the same goal: seamless communication between devices over a network. The table provides a detailed comparison between the OSI Open Systems Interconnection model and the TCP/IP Internet model, highlighting their structural differences, design approaches, and key characteristics. Layer structure. OSI model consists of 7 distinct layers, each with clearly defined functionalities such as presentation, session, and application. TCP/IP model has the simplest structure with 4 layers, combining some OSI layers into broader categories like the application layer concepts. OSI model explicitly separates services, interfaces, and protocols, making it a more conceptual and comprehensive model for understanding network communication. TCP/IP model. This model does not clearly distinguish between services, interfaces, and protocols. It is more focused on practical implementation design approach. OSI model. This was created as a theoretical framework before the actual development of protocols, making it more of a guideline for network design. TCP/IP model was developed alongside the protocols. It describes making it a more practical and implementation-driven model. Connection support. It was developed alongside the protocols. It describes making it more practical and implementation-driven. OSI model supports both connection-related and connectionless communication in the network layer, but the transport layer is strictly connection-related. TCP/IP model. This model offers connection-related TCP and connection list. Protocol dependency. OSI model is protocol independent, meaning it was not tied to any specific set of protocols, making it more general-purpose TCP/IP model. This is protocol dependent, designed around protocols like TCP and IP. Credibility and interneting. OSI model. This is considered less credible for practical implementation as it does not directly support interneting. TCP/IP model is more credible and widely adopted due to its robust support for interneting, making it the backbone of the modern internet. Let us summarize what we have studied on this topic. The OSI Reference Network Model. The OSI model is a 7-layer theoretical framework that standardizes network communication by dividing it into distinct layers with the specific functions. It is primarily used as a guideline for designing and understanding networking systems, but is less commonly implemented in real-world scenarios. TCP/IP Network Model. The TCP/IP model is a 4-layer practical framework developed alongside its protocols, focusing on real-world implementation for internet-based communication. It is a foundation of the modern internet, offering flexibility and reliability through connection-oriented and less protocols. Comparison between OSI and TCP/IP network model. The OSI model is more detailed and conceptual, with clear distinctions between layers, services, and interfaces. While the TCP/IP model is streamlined and practical, the TCP/IP model is a protocol-dependent and widely used for interneting. Thanks for watching. Visit Blacksnwhite.com. Learn today, lead tomorrow. Don't forget to like, share, and subscribe for more tech updates. Stay inspired, keep learning, and grow with us.